Hello dear friends. In this lecture we will continue our discussion on ILP algorithms. We were talking about the branch and bound algorithm. We made an example in the previous lecture. Today we will learn about the candidate solutions and parent bounds, parent and child relationships between the branch and bound nodes, and we will make more examples. So let's get started. The first thing that we will learn in this lecture is the concept of candidate solution. In fact, the candidate solution is an integer feasible solution, nothing else. Okay? During the branch and bound search, whenever you solve a subproblem in one of the branches, remember, in branch and bound, we always solve linear programs. All problems that we solve are linear programs, and we solve them using the simplex algorithm. But sometimes the solution to these linear algorithms can be integer feasible. Okay? So whenever we have an integer feasible solution, then that solution is named as a candidate solution. Okay? So this is the meaning of candidate solution. Now, look at this example. And branch and bound tree is given to us, and it's asked in this branch and bound tree which nodes represent a candidate solution. Okay, let's start from the first node. Remember again, in a candidate solution, we need to have an integer feasible solution, and in this example, there are two decision variables x1 and x2, and both of them are integer restricted. Okay, so this is the root node and the LP relaxation. You see the solution is not integer. So this is not a candidate solution. And be careful, we have three reasons for fathoming a branch. What are they? Fathom because of infeasibility, fathom because of bound, and lastly, fathom because of integer feasibility. Okay? So if you have a candidate solution, it means that you need to fathom that node. Therefore, in fact, if we are searching for a candidate solution, you only need to look at the nodes which are fathomed, which are not branched. And you don't need to look at the root node because it's branch. You don't need to look at this node too because it's branch. Okay, so let's look at the fathomed nodes. Node 3 is fathomed, but the reason for fathoming is infeasibility. It's not integer feasible, so this is not a candidate solution. Again, node 5 is fathomed because of because of infeasibility of this LP subproblem, and this is not a candidate solution. Node 6 is fathomed, and when we look at the solution here, it's integer feasible. So this is a candidate solution, and since this example is a maximization problem, this objective function value here provides us a lower bound. And finally, let's look at node 7. It's also fathomed, and you see x1 and x2 are both integers. It's integer feasible. So this is also a candidate solution, and the objective function value here provides a lower bound for us. And when we compare this lower bound with the previous lower bound, we see that this is a better lower bound. Okay, a higher lower bound means a better lower bound, and so this is a candidate problem. So in this branch and bound tree, the candidate problems are this one that we obtained in node 6 and this one that we obtained in node 7. Another important concept related to the branch and bound algorithm is the concept of parent bounds. Okay, so the name of the algorithm is branch and bound, and in this algorithm, calculating bounds are important, and parent bounds are one way of calculating bounds. But the first thing we need to understand what a parent is. Okay, a parent, whenever a node is branched, this node, the branched node, becomes a parent, and the new subnodes are called their children. Okay, so node 2 and node 7 are the children of node 1, and node 1 is the parent of these two. Similarly, node 2 is the parent of node 3 and 4. And in another perspective, node 5 and 6 are children of node 4. Okay, so if you look, for example, node 2 is the parent of node 4, and node 4 is the parent of node 5 and 6. In this perspective, node 2 is the parent of node 5 and 6 as well. Okay, and so we do not just look at the directly relationship between parents and child, but the parent of a parent is also named as the parent node. Then, what's parent bound? Remember, when we branch a node, we add a constraint to the problem. For example, when we branched this LP1, on this side for node 7, we included x1 less than or equal to 3 as a constraint to the problem. And on this side, we included x1 greater than or equal to 4 to obtain LP3. So when we compare LP1 and LP2, in LP2 we have additional this constraint, and in LP1 we don't have that constraint. In this perspective, a parent is a relaxation of its children. So this LP1 is a relaxation of LP2. In LP2, if we delete this constraint, we come up with this one. So LP1 is a relaxation of this. Similarly, in LP3, if we delete this constraint, x1 greater than or equal to 4, then we obtain LP1. So LP1 is a relaxation of LP3, right? So a parent is a relaxation of its children. And similarly, look, LP4 and LP3. LP3 is a relaxation of LP4 because in LP4, if we delete this constraint, then we obtain this one. And in LP3, if we delete this constraint, we obtain this one. And it means that LP1 is a relaxation of LP4 as well. Okay, so we know from our discussion on relaxations and the use of relaxations, a relaxation always provides a better optimal objective function value than the model that it relaxes. In this sense, since a parent node is a relaxation of its children, then the objective function value of a parent must be better than the objective function value of its children. Okay, given this information, now let me ask you this question. If you don't know the objective function of this problem, can you determine the objective function? I mean, is this a minimization problem or a maximization problem? So you need to look at the parents and childs. Look, this is the optimal solution of node 1, which is 23.75. This is the optimal solution of LP2, one of its children, it's 23. And when you compare, you see 23 is less than this value. Similarly, look at node 2. The objective function value is 23.33, which is less than this value. Okay, we said that this is a relaxation of these two nodes. Then the objective function value of a relaxation must be better than its relaxations, the original models. And better means that in this case, the problem here should be a maximization problem, okay? It's a maximization so that the relaxed problem has a higher objective function value than the original ones. Okay, similarly, let's consider LP3. Okay, LP3 is the parent of LP4 and LP5. The objective function value of LP4 is 22.5. Okay, you see the objective function value of the parent is higher than its child. So don't look at the infeasible solutions because they don't have any feasible solutions. Okay, just look for the feasible ones. Similarly, When you look at the children of node 4, the objective function value here must be higher than its children. As you see, its children has an objective function value of 20, and this is 22.5. It means that the parent has a better objective function value. And since objective node 2 is the parent of node 5 and 6, its objective value is higher than the objective value of node 5 and 6. In fact, 5 is infeasible, but node 6 has an objective value of 20, and this is 23.33. So for a maximization problem, this value is larger. If this was a branch and bound tree for a minimization problem, then we should have the opposite. So this value would be less than this value, and it would be less than this value. Okay. So you see in this branch and bound tree between some nodes there are no parent-child relationship. Look, for example, this node 2 and node 7. There is no parent-child relationship. Therefore, we cannot say anything about their objective function values. We cannot know which one will be greater than the other one. Similarly, node 7 and node 3 or node 7 and node 4 does not have any parent-child relationship. Therefore, we cannot say that this node's objective value will be higher or lower than this one. It can be both of them. Okay, the parent bounds only related with the parent-child relationships and parent of parents. Okay, so on the other hand, this node, root node, is the parent of all other nodes in the tree. And it means that the objective function value of root node must be better than any of the nodes in the branch and bound tree. It can be equal or it can be better. So in a maximization problem, better means larger or higher. So this 23.75 shows us the maximum possible value that this integer program may have. And if you look the objective values of all other branches, all other nodes, you see that all of them are less than or equal to this value. Okay, after learning these parent bounds, then we can make use of it during the branch and bound search to calculate the lower and upper bounds for our problem. Okay, so how we can do? Let's consider the example problem. This is a maximization problem. Okay, and we start with the LP relaxation, which is the root node. And since this is the maximization problem, the branch and bound algorithm sets the initial lower bound, which is the best known objective function value of an integer feasible solution, to minus infinity, because we don't know any. Okay, so we start with minus infinity. And then we solve the LP relaxation, and we get the objective function value of 23.75. Then, what are the lower and upper bounds in the first node? Since we don't have any integer feasible solutions, that is, we learned that integer feasible solutions are candidate solutions. Since there are no candidate solutions, the lower bound is minus infinity. And the upper bound is the value, objective function value of the all the parent bounds. Okay, so all the open, not explored parent bounds. And for the first one, this parent bound is 23.75. So initially, my lower and upper bounds are like this. So what does it mean? The maximum value of this integer program will be 23.75. This is the maximum possible. And if it is infeasible, if the model is infeasible, the minimum value will be minus infinity, and currently we don't know if it is feasible or not. Okay, and then we continue to explore the children of this root node. After branching the root node, we have two open nodes, and we select one of them. We randomly selected this node 2 as LP3, and we solve it. When we solve it, again, the result is not integer. Since it is not integer, and since until now we couldn't find an integer solution, a candidate solution, our lower bound does not change. It's still minus infinity. But in order to calculate the upper bound, what do we have? We need to look at all the unexplored nodes. So currently this node is unexplored. We will explore it, we will branch it, and the maximum possible value that we can get from this side of the branch and bound tree is 23.33. And this is also another node that we didn't explore, and the maximum possible value that we can obtain from this solution is given by its parent. It's 23.75. Okay, so this parent provides a bound for this, which is 23.75. So it means that if we go from this side, we can find a bound, we can find a solution of 23.75. If we continue from this side, the best we will find is this value. It means that from this all over problem, the best possible, the maximum possible objective function value that we will obtain is 23.75. That's why our upper bound at this point is 23.75. It means that it's not changed from node 1 to node 2. Okay, then we decide to branch node 2, and we come up with two children, and we select one of them and solve it randomly. So we solve node 3, and the result is infeasible. This LP5 does not have a feasible solution. Then, since we didn't get any integer solution until now, our lower bound is still minus infinity. And in order to find the upper bound, we look at the unexplored nodes. The currently unexplored nodes are node 4 and node 7. So for node 4, what is the best possible value, objective function value that we can get? And we should look at its parent for this purpose. And its parent says that you can get the maximum, 23.33. Okay. The other unexplored node is node 7. And what is the best possible value that we can get from this side? When we look at its parent, it's 23.75. So the upper bound will be the maximum of these two values, which is 23.75. Okay, so the lower and upper bounds after solving node 3 are still the same. In the next step, we solve the problem in node 4, and when we solve it, we found the solution which is not integer feasible, and its objective function value is 22.5. Then at this point, what are the lower and upper bounds? Still, we didn't get any candidate solution, any integer feasible solution. Therefore, the lower bound is minus infinity. And as unexplored nodes, the best that we can get from this side is 22.5. And the best that we can get from this side is given by its parent, which is 23.75. Therefore, the upper bound is 23.75. In the next step, we solve node 7. Okay, and when we solve it, there are no feasible solutions. In fact, during the branch and bound tree, if a branch is fathomed because of infeasibility, then the lower and upper bounds usually does not change. So still we couldn't find any integer feasible solution. Therefore, the lower bound is still minus infinity, and the upper bound is given by the unexplored nodes. So there are two unexplored nodes, this one and this one. So from this node 6, the best that we can obtain is given by its parent, which is 22.5, and for these node 7, the best value that we can obtain is given by its parent, which is 23.75. So the upper bound will be the maximum of these two values, which is still 23.75. Next, we solve node 6, and when we solve it, we see that we come up with an integer feasible solution. This is a candidate solution, okay? And in this candidate solution, the objective function value is 20. So now this 20 provides a lower bound for us. The previous lower bound was minus infinity, and we found 20. So we are trying to maximize, and for a maximization problem, 20 is better than minus infinity. Therefore, we update our lower bound to 20. And what about the upper bound? Okay, so this node is fathomed because of integer feasibility, and the only node remains unexplored is node 7. And the best possible that we can obtain from node 7 is given by its parent, which is 23.75. So this is the upper bound. Then, after solving node 6, we know that the lower bound of this problem is 20, and the upper bound of this problem is 23.75. Look, this is very important. The branch and bound is not completed yet. It's not completed yet. But we already have a solution, integer solution, which is 20. So sometimes we may decide to stop at this point without exploring the remaining nodes. We stop at this point. And if we stop, we have an integer feasible solution, and we know that this integer feasible solution deviates from the best possible solution by this difference, okay? 23.75 minus 20. Okay, so if that difference is too small, then you don't need to consider the rest of the branch and bound tree. You may just decide to stop, because considering the rest of the branch and bound tree may require a lot of time. Okay, in this case, if you stop early in branch and bound, before fathoming all unexplored nodes, then the branch and bound becomes a heuristic algorithm, but it provides you the error. Okay, so having that information is very useful. Okay, then we solve the only unexplored node, which is node 7. And when we solve it, we see that we come up with a new candidate solution. All decision variables are integer, and its objective function value is 23. Okay, initially the objective function value was 20. When we solve it, we found the solution with objective function value 23, and we are trying to maximize. So for a maximization problem, this 23 is better than 20. Therefore, we update our lower bound from 20 to 23. Okay. What about the upper bound? The upper bound is provided by the unexplored nodes. And now, since we fathomed this node because of integer feasibility, there are no unexplored nodes, and then the upper bound becomes equal to the best integer solution, which is 23. Okay, it's always the case. When the branch and bound algorithm stops, this is very important. Okay, when the branch and bound algorithm stops, the final lower bound is always equal to the final upper bound. There is no difference between these lower and upper bounds. Okay, now please stop the video at this point and try to answer these questions by yourself. And then after having your comments, we will continue our discussion. Okay, I believe you stopped it, worked on it, and now let's consider the questions all together. The first question says that, so for this branch and bound tree, is this a minimization or a maximization problem? Okay, how can we understand it? For this purpose, we will look at the parent bounds. Okay, we will look at the root node and its parents. We will look at one node and its parents. Remember, a parent is a relaxation of its children, and therefore the objective function value of a parent must be better than its children. Okay, let's have a look at this. 165 divided by 4, basically it's 41.25 something. Okay, 41.25, and the children has 41 and 39. So this is larger than this one and this one. So larger should be better. So is this a minimization or a maximization problem? Of course, it is a maximization problem. Similarly, if you look to the other ones, for example, look, this one is 41, and the son and its child has 40. So 41 is larger than 40. It means that this should be a maximization. Okay, so in a maximization problem, when you go downwards in the branch and bound tree, you will see that the objective function values will never increase. Either they will stay the same or they will reduce. In a minimization problem, it's opposite. When you go from the root node to the other branch, the objective function value will either be equal or larger. Okay? So this is the first question. So part B asks for the optimal solution and in which node we encountered this optimum solution. Okay, in part A we understood that this is a maximization problem. Then, in order to find the optimum solution, we need to look for the candidate solutions and we need to look for the fathomed solutions, okay? The fathomed branches. And which branches are fathomed? If you look, this branch is fathomed, this branch is fathomed, this one is fathomed, and this one is fathomed. Okay. Then what are the objective values or what are the reasons for fathoming? You see this is the reason of fathoming of this one is infeasibility. So it means that we cannot get the optimum solution from this one. Okay. The reason of fathoming subproblem 6 and 7 are because we obtained candidate solutions. And similarly from subproblem 3, we also obtained a candidate solution, integer feasible solution. Then let's check the objective values. The first one, this one has an objective value of 40, this one has an objective value of 37, and this one has an objective value of 39. And among these, the maximum is given by this node. Okay, so this is the branch that we encounter the optimum solution, and the optimum objective function value is 40, and the decision variable values are 5 and 0. In part C, we are asked about the lower and upper bounds at each node of the branch and bound tree. So for this purpose, we need to know the sequence of the branch and bound tree, in which sequence we explored these nodes. And in this example, that information is given with this. T equals 1 here. It means that it is the first node that we explored. Then we explored this one, second, third, fourth, fifth, sixth, okay, and seventh. Okay, then we start from the first one. Since this is the maximization problem, the lower bound is set to minus infinity. Okay, so this is the lower bound. And the upper bound is given as the objective function value here, which is 165 divided by 4, which is 41.25. So we can write 41.25. Okay, so this is our upper bound. Then secondly, we explore subproblem 2, and we couldn't find an integer feasible solution because x2 is non-integer. Therefore, the lower bound is still minus infinity, and the upper bound is okay. Upper bound comes from the parent bounds of the unexplored nodes, and from this side the best possible that we can get is 41, but from the other side, from this side, the best possible that we can get before solving, remember we didn't solve, we don't know these values, it's unexplored yet, we will find it later on. Okay, the best possible will be given by its parent, and its parent is this one, so the upper bound is still 41.25. 41.25. Okay, then we explore this subproblem 4 as the third node, and since it's infeasible, the lower and upper bounds do not change, and the lower bound is minus infinity and the upper bound is 41.25. okay, this is 25. Then we move to the next node, which is subproblem 5. Okay, and we find the solution, but it's not integer feasible solution. Still we don't have any candidate solutions, therefore the lower bound is still minus infinity, and the upper bound, okay, it is the best possible that we can obtain from the unexplored nodes. From subproblem 5, the best possible that we can obtain is this, but on the other hand, the best possible that we can obtain from subproblem 3 is given by its parent. Therefore, the upper bound is still 41.25. Okay, then the next node that we explore is this one, subproblem 7, and when we solve it, you see we come up with an integer feasible solution, a candidate solution. It means that we compare the objective function value of this one with the previous, which is minus infinity. And since this is a maximization problem, 37 is better than minus infinity. So our lower bound becomes 37. Okay, and the upper bound, okay, upper bound is the best possible that we can obtain from the unexplored nodes, and the unexplored nodes are subproblem 6. So for which the best possible that we can obtain is coming from its parent, and subproblem 3 for which the best is coming from its parent, and therefore still we have 41.25 as the upper bound. Look, at this point, if you stop the branch and bound 3, the algorithm, you will end up with a solution with objective function value of 37. This is integer feasible. And you know that this solution deviates from the best possible by only 4.25%, the difference between these two values. Okay? But if you continue, you may find a better or good solution, or you may end up with the same solution. We don't know it. In order to understand, you need to continue. So in the next step, we find or we continue with subproblem 6, okay, and we see that this is also an integer feasible solution. Its objective function value is 40. The previous best solution was 37. For a maximization, 40 is better, so our lower bound moves to 40. We update the lower bound from 37 to 40, and our lower bound comes from the unexplored nodes, and subproblem 3 is still unexplored, and its objective function value, best possible value, comes from its parent. Therefore, if we stop here, let's say, the best possible that we can have is 40, and we know that it deviates from the optimal solution by 1.25 only, the best possible solution. But still, maybe there's a better solution, or maybe this 40 is the optimal. We don't know. We need to continue until to the end if we want to find the optimum solution. Otherwise, if we are okay with this error, then we can stop at this point. Okay? So the next unexplored node is subproblem 3 here, and when we solve it, we see that we come up with a candidate solution, integer feasible solution, you see? And the objective function value of this solution is 39. And when we compare this with the previous one, which was 40, the previous is better than this one. So we don't update our lower bound. We update the lower bound only if it is better than the previous alternative. Okay. So therefore we stop at this point, and the lower bound here is still 40. Sorry. Okay. And the upper bound. Okay. Are there any other unexplored nodes? No, there are not, and since this is an integer feasible solution, we fathom this node as well. So this is the final node. It means that the upper bound should be equal to the lower bound, which is 40. Okay, so these are the upper and lower bounds. Okay, before part E, let me clean everything here. And in part D, it says that which nodes are branched. And it's easy, as you can see. This root node is branched. Okay, subproblem 2, this node is branched, and this node is branched. So this node 1, node 2, and node 5, we can say they are branched. Okay, in part E, it asks which nodes are fathomed. And if you see subproblem 3, this one, subproblem 4, this one, subproblem 6 and subproblem 7, they are fathomed. And it asks for what are the reasons for fathoming. By the way, be careful, this subproblem 3 does not indicate the order of exploring this node. As I said, we explored this node as the 7th node. Okay? This is the name of the problem, but this is the order of the problem that we explore it. Okay, what is the reason of fathoming, let's say, this node 3, this subproblem 4? It's given here. It is because of infeasibility. Then what's the problem? What's the reason of fathoming this node 5, which is subproblem 7? Because we found an integer feasible solution, fathom by feasibility. Okay. What about the next node, node 6, subproblem 6? What's the reason of this fathoming? Again, we found the candidate solution, an integer feasible solution, and the reason is fathom because of feasibility. And finally, what's the reason of fathoming this node 7, which is subproblem 3? In fact, here we can write two reasons. The first reason is we found an integer feasible solution, and we can fathom because of feasibility. That's one reason. But there's another reason here. If you look carefully, even, for example, these values of the decision variables, if they were not integers, if x1 was not 3, but if it was, for example, 2.7, still we would fathom this. And the reason would be fathom because of bound. Why? Look, the objective function value of this is 39. And this is the parent. If we decide to branch it, this would be the parent of all others. And we know that the parent is the best of its children. Okay? So this says that if you go further down from this node, the best possible value that you will obtain is 39. But from our previous node, we know that we already have a solution with objective function value 40. So even if we explore this site further, we will not be able to find a better solution. In that case, we fathom because of bound. Okay? So for this last one, you can write two reasons, either fathom because of integer feasibility or fathom because of bound. Both of them are okay. Okay, now it's time to test yourself if you can solve a problem using the branch and bound algorithm or not. So please work on this example. Try to solve this problem using the branch and bound algorithm. You see, it's a problem with two decision variables. It means that you can calculate the optimal solutions using the graphical solution method. It means that you need to sketch the feasible region, okay, and then try to solve it. Please stop the video at this point and try to solve this problem using the branch and bound algorithm by yourself. And in the next slide, I will give you the solution, the branch and bound tree. Okay, I hope you worked on that problem by yourself. Maybe you could you could find the solution. Maybe you encountered some problems and you couldn't find. Please have a look at this solution and try to understand your mistakes and then try to do it by yourself. By the way, your branch and bound tree may be different than this one, depending on the choices that you make during the branch and bound tree. For example, after finding the initial solution here, both x1 and x2 are non-integers. So in this tree, we decided to branch on x1. But if you decided to branch on x2, you will have a different tree. Okay? So it's not wrong, it's not mistake. It can still be the same, it can still be correct, but the thing is, at the end of the algorithm, the objective function value that you have found must be identical to the optimal objective function value of this one, which is this. The optimum solution of this branch and bound tree is given here. So x1 should be 4, x2 should be 2, but more important than that one, the z value should be 14. You may end up with a solution with objective function value equal to 14 with different x1 and x2 values. It's okay, no problem. But the objective function value should be 14. If you end up with something else, then it's wrong. Okay, so as I said, depending on your choices, you may have a different shape, different branch and bound tree. But in that case, if that's the case, please try this version as well by yourself. Try to branch on x1 first and then continue in this way, and let's see if you can find the same solution or not. Okay, so this is the solution. By the way, the lower and upper bounds are not provided here, but it's a good method to write the lower and upper bounds at every node while solving the problem. Please do it by yourself again. Try to write the lower and upper bounds at each node of this branch and bound tree. Okay. Okay. Now another example, another practice for you is, let's repeat the same problem, but this time let's assume that here in the model x1 and x2, both of them were integers. But let's assume that only x2 is integer. x1 is a continuous variable. Okay? Let's try to solve the problem with this assumption, and let's try to understand how we can solve how the problem changes. So, okay, this is the solution. We start again with the LP relaxation with the root node, and when we solve it, we end up with this solution. You see, x1 is non-integer and x2 is non-integer. But remember, x1 is continuous. It is not an integer restricted variable. So if you go and branch on x1, it will be wrong. Okay, we should consider only the integer variables on branching. That's why we branch on x2, x2 less than or equal to 2 and x2 greater than or equal to 3. So we include these constraints one by one to the LP relaxation and solve it. You see, when we force x2 to be less than or equal to 2 and solve it, we end up with this solution. And okay, let me first go to the other side. We initially solved this right hand side. Okay, so when you add this constraint and solve the problem, you see that we end up with this solution, and we need to make a decision here. Should we stop fathom or should we branch? And if you say, okay, we need to branch because x1 is not integer, then it is wrong. Again, x1 is not integer restricted. Only integer restricted variable is x2, and its value is already integer. So we stop here, we fathom because of integer feasibility. Okay, so this is a candidate solution, and our lower bound becomes 13.5. This 13.5 is a lower bound. And what's our upper bound? The upper bound comes from the parent of unexplored nodes, and the only unexplored node is this one, and its parent is the root node, so the upper bound is 14.47. Okay, so at this point we have these lower and upper bounds. Then we explore the next node, and we see that when we solve it, we come up with this solution. X1 is again non-integer, but it's not a problem because it's not integer restricted. X2 is integer, that's fine. And therefore we stop. This is also a candidate solution, and its objective function value is 14.4. Our previous lower bound was 13.5. And for a maximization problem, 14.4 is better than the other one. So we need to update our lower bound to 14.4. Okay, so we stop at this point. We fathom because of having feasible solution. And since there are no unexplored nodes, the upper bound should be equal to the lower bound, which is 14.4. So this solution is the optimum solution. You see, although x1 value is non-integer, it's not a problem because in the problem it is not integer restricted. Let's continue working on the same example, but this is an homework for you. Please study by yourself. And this time, let's consider x2 to be continuous. Okay. So only x1 is integer restricted, x2 is continuous. Then I want you to solve this problem in two alternative ways. In the first one, please solve the problem. Okay, when you solve the root node, you will most probably end up with an x1 value which is non-integer. Then you will branch it so that x1 will be less than or equal to some value on the one side, and on the other side x1 will be greater than or equal to some value. Okay, so which one to select? So in the first alternative, please first select this side and continue from that node and solve it, and finish the branch and bound tree. In the second alternative, please go from the other side and first explore this node and then finish the branch and bound tree, and try to see how long does it take, how many branches, how many nodes do you need to explore in each case. Okay, so we will continue our discussion on branch and bound tree in the following videos.